You're a high school chemistry teacher, and you're about to tackle with your students the following question. Why does the temperature not change while stuff freezes? You have the option of showing your students either the cooling curve, or in this particular case, the heating curve of water, which shows you exactly that while freezing, or in this case, melting is occurring, the temperature is not changing. But how can you have your students figure this out themselves experimentally? Is there a simple experiment that you can do with your students that shows them that during that solidification process, the temperature rests in peace and changes very little? And can you add it to the next level by including a solute and a solvent and watch that freezing temperature drop? Can you again have your students figure this out experimentally at the regular chemistry, not the AP chemistry level? Why not? You don't really want to get into all the formulas associated with colligative properties, as shown in this awesome video of the organic chemistry tutor. You may want to go into molarity, but do you really want to delve into molality? Again, as shown in this video of the organic chemistry tutor. There are plenty of beautiful videos out there, especially this one, that involves the determination of the molar mass of the solvent. This particular video shows you very nicely how you can use benzoic and lauric acid, a hot plate, test tubes, and a beautiful temperature probe to take all the measurements, just so. Very fancy equipment that I personally do not have in my high school chemistry classroom, with this continuous stirring happening of the lauric acid in the test tube. And look at this beautiful curve, cooling down until freezing starts. In this video, I'm going to show you my version of the freezing point depression lab. This is my handout, which includes a clear purpose, the organic structure of the two chemicals involved, a student-directed safety procedure, and the actual procedure for carrying out the lab. This particular lab deals with the following NGSS standards and New York State Science Learning Standards, namely HSPS 1, matter and its interactions. And for those of you in New York State, it particularly addresses HSPS 1-10 solutions. Use evidence support claims regarding the formation, properties, and behaviors of solutions at bulk scales. Patterns. Here's a picture of my setup in my fume hood. I've been using pretty old batches of benzoic and lauric acid, but it works. And I should note that I recycle the pure lauric acid and the lauric and benzoic acid tubes every year. So I never waste any of these relatively hazardous chemicals. I heat up the test tubes in my fume hood to roughly 70+ degrees Celsius. If preferred, you can heat them up all the way close to 100 degrees Celsius. Once the students receive the test tubes, they have to vigorously stir, preferably while holding the test tube. They receive a Google Sheets document from me that enables them to collect all their data. And once they've collected all their data, they're able to create a chart very much like the one shown on this screen. All you do is simply highlight the 3 columns and go to Insert Chart, and you've got a chart very similar to the key that I just showed you. You want to show the actual dots that reflect the data, go to Customize, Series, and increase the point size to however high you wish. And there's your chart. Let's copy that chart over into the Google Doc where the lab handout actually is. Here's the lab handout, and in the space for the hyperlinked Google Sheets chart, you just click Ctrl-V, and there's your chart. Now I have them do this twice, once in the hyperlinked Google Sheets chart, and a second time in the annotated Google Sheets chart. The second time, they paste their chart unlinked. The reason for this is that they can then click on that unlinked chart, hit Control-Copy, and then travel to the Insert Drawing tool. If you click on Plus New, and then click on Control-V, you can now manipulate this chart and annotate it. what I guide them to do is to figure out the freezing point of just lauric acid, figure out the freezing point of lauric and benzoic acid, and determine the freezing point depression. I also guide them to which portion of this chart shows a decrease in kinetic energy and which portion of this chart shows an actual decrease in potential energy. And once they've annotated that chart, they can just hit Save and Close, and all the work is there. This shows you the actual key of that annotated Google Sheets chart. Some great follow-up questions after they've completed their experiment and their data analysis is shown in the following page of the handout. And I'm referring here to the GIF animation on the right, which visualizes water molecules that are concentrated around a chloride particle. And students can then answer some questions related to that. The fact that it is a liquid, not a solid. The fact that they're looking at a mixture, not a pure substance. The fact that there are hydrogen bonds that encourage the water molecules to stay connected. And the fact that the chloride ion is the actual solute versus the water particles being the solvent. And the next level up would be to maybe address the ion dipole forces between the chloride anion and the water molecules. Then you can connect those questions relating to chloride in water to the actual lauric acid and benzoic acid experiment. And this enables students to ponder over the idea that there could be solvation shells, not hydration shells, but specifically solvation shells involving the benzoic acid solute and the lauric acid solvent particles surrounding it. And as this key demonstrates, the dashed lines are reinforced because of the hydrogen bonds made possible by the carboxyl groups present in both lauric and benzoic acid. This freezing point depression lab handout ends with two focus questions. One question that asks them to explain how they determined the freezing points for both lauric acid and the solution between lauric and benzoic acid. And the second question asks them to explain the difference between the freezing point for pure lauric acid and the freezing temperature of the solution. We are here at the website of the American Association of Chemistry Teachers, and this particular simulation involves colligative properties. And I'm going to scroll down and show you what students can now investigate. So in terms of solutions, there are three options: sucrose, sodium chloride, and magnesium chloride. Obviously, if we start with sucrose and we click on freezing temp and run the experiment, then we can see that in comparison to the control, which shows you just pure water, and the max 3 moles of sucrose in solution, there's a temperature drop of well over 5 degrees Celsius. If we reset this and now click all the way down to magnesium chloride, which, as us chemistry teachers know, that releases 3 particles per formula unit of magnesium chloride, and we click on freezing and run the experiment again, we now see a whopping, wait for it, drop of almost 17 degrees Celsius when 3 moles of magnesium chloride has been added to presumably a liter of solution. In my opinion, you can even have them do this simulation before you have taught your students about molarity. Here I've taken screenshots of the 3 different solute options: sugar, salt, sodium chloride, and salt, magnesium chloride. And what you're noticing, as a greater number of particles are present in solution, the greater the drop in freezing temperature. And alternatively, they can do the same for the boiling temperature. Let's recap what we've talked about in this video. The central question is, why does the temp not change while stuff freezes? I'm going to focus on 3 takeaways. First question, why does the temp not change when stuff is freezing? As you can see in this awesome YouTube video, the liquid water molecules as modeled in these two water molecule magnets, they are attracted to each other. So instead of moving more slowly during the freezing process, they are actually going to connect with each other through hydrogen bonding. The second question, why does the freezing temperature drop when a solute is added to a solvent? This is because the forces between the solute, in this case chloride, and the solvent, in this case water, are impeding the freezing process. Because when stuff freezes, water needs to hook up with water and not with the solute particles. Thirdly, what determines how much the freezing temp drops when a solute is added to a solvent? As we saw in the simulation, it is based on the number, not the type of particles that the solute releases in solution. For sugar, that is only 1 per sugar molecule. For sodium chloride, that is 2 per formula unit of NaCl. And for magnesium chloride, that is 3 particles per unit of MgCl2. Therefore, magnesium chloride drops the freezing temp even further. The topic of this video, centered around freezing point, is very much related to a project-based learning module that I'm currently working on with my students, centered around the question, why does it matter what's in the water? Stay tuned for a video that I'm going to be producing centered all around this particular PBL module. If you're interested in this particular lesson handout on the freezing point depression involving lauric and benzoic acid, or any other of my science handouts, simply click on the link in the video description below. And in exchange for your email, you will get the Google document to all my resources as well as the teacher keys. Dutch lesson for today. Why does the temp not change while stuff freezes? Here's the whole sentence in Dutch. Waarom verandert de temperatuur niet tijdens het vriezen? Let's do that one more time and a little bit slowly. Waarom verandert de temperatuur niet tijdens het vriezen? Try it out. Thank you very much for watching. Bedankt voor het kijken. Tot ziens and see you in the next video.